на уговоры. Давайте по-английски говорить. И, ну, вроде бы все. С другой стороны, тогда забавно, зачем вообще приходить на лекции, если можно потом смотреть кино. Так, ну все, тогда мы начинаем. Я выключаю свою камеру. Я бы сказал, что у меня два экрана, и у меня здесь камера, и здесь камера, и поэтому мне легче ее выключить, чтобы не видеть самого себя и не отвлекаться на камеру. Я выключаю. Так, это лекция 4. Надеюсь, надеюсь, вы экран видите, да? Написано лекция 4. Hello? Can you see the screen?
Yes, we can see.
Okay, great. All right, let's start. So that's where we stopped last time. So we consider now at least three-dimensional slow, fast neuronal models. Okay, so we have two fast variables and then one slow. So basically, a slow variable here is z, right? It's on a horizontal axis, and we assume for simplicity again, it doesn't have to be always like that. But if you do want to consider endogenous bursters, then eventually you would need this kind of hysteresis. You see that hysteresis or overlap? Okay, so in a typical in a Fitzhugh-Nagum model, you have hysteresis between two stable branches, upper branch and lower branch. Okay, and unlike two-dimensional system, the third dimension gives you an extra degree of freedom, so to speak. It's not extra degree of freedom; it's just an expression. Okay, and the idea is that, all right, so what we can do, it's not just what we can do. The truth is that that's what basically happens in some neuronal models, okay? And it's really, really interesting that you have the same set of ingredients, right? You have a Hodgkin-Huxley model of neuron, right? It's based upon Hodgkin-Huxley formalism, right? It's like your kitchen, you have a fridge, right? You would like to cook something for tonight, and then you have ingredients, and you can do either one particular meal, or you can use the same ingredients, you can try a different meal. Okay, so that's what makes it very interesting, that depending on certain currents and the temporal characteristic of currents, you get an interesting variety of topological configurations that can be sketched, like in my slide right now, right? And they give you different types of activity. Again, at this point, it's just, what you see is just a geometric approach, right? So in this case, we assume that these are neuronal bifurcation we needed to create this cylindrical surface, okay? Like this or like that cylindrical surface. We need the branching periodic orbits. So in English, we would say that that this is called a slow motion manifold. This is slow motion manifold, one, okay? And then you exponentially fast converge from a saddle node onto this attractor, so it's a fast transition, and then you turn around this two-dimensional manifold, slowly shifting to the right. Okay, this is only true if I place the slow null line, the equation for the where z prime vanishes, right? Z prime again is the direction along the z-axis, right? So by construction, we create z prime so that z prime is going to be negative along the lower branch, and z prime is going to be positive above the upper branch. So you can kind of transition freely but slowly towards along that manifold, right, until you reach the termination point, which can be what's called a reverse neuronal bifurcation, like in this particular case, right? After that, you transition through this bifurcation, or through this point, tipping point, it's called, right? And then you just converge to the stable branch by construction, right? It's stable again. It used to be unstable between these points. And then you jump quickly. When I say quickly, we mean exponentially quickly from the ghost of the saddle node onto the branch of this equilibrium state. So it's called metastable state, right? Metastable means you transition through that state, right? And then you're going to get plateau-like bursts like this, right? And the truth is that they do exist, right? They do exist in various systems, right? And sometimes I mean, again, I have a paper. I mean, I mentioned that to you one day that this is a highly the model what we consider it has I think 14 or 16 differential equations. So one is a voltage, and all other variables, they are getting variables, right? They describe the probability whether some channels are open or closed, plus calcium. So we call this biologically plausible or accurate or exact model. When I say exact, it doesn't sound like, what do you mean exactness? Can it be improved? Very likely, yes, but I mean, but you reach some kind of saturation. You don't have to improve it anymore. It's already so accurate and precise. Okay, and let me just comment that a friend of mine who studies what's called myocyte dynamics. Myocyte is the cells that the heart is made of, right? They're called myocytes. And those cells, all they have to do is just generate just a single action potential. That's it. But his models are super highly precise. Each model includes like around 70 or 90 differential equations plus some other differential equations written in the form of the Markov process. And the only reason why, I mean, to generate just a single spike, I mean, why do you need so many equations, right? But he works with pharmacological companies. So basically his models, what's called of transgenic mice, right? Transgenic, very special mice, right? They're designed for experiments, right? So they test how different chemistry or basically drugs or medicine affects the dynamics of the heart. Okay, so that's, I mean, different applications, right? But even though it can be, phenomenologically reproduced by a three-dimensional model that's called Ludi, I forgot the name, Ludi, whatever. All right, so the next type of model, right, that also super typical in neuroscience, right, describe what's called square wave bursters. So for us, square wave burster basically means that you have the same configuration, but in contrast to the previous case, right, the branch of the periodic orbits terminates through the Hammer-Klinic bifurcation like that, right? And what is shown here, this line is called average V. So basically, so think of this, right? You have a limit cycle like this one, right? And then you would like to find the gravity center of the limit cycle. So how do you do that? All you do, you suppose you have all these coordinates, right? And then you average, right? You add them up, all of them, right? And then average with respect to number of points or with respect to the period of the periodic orbit, and you will get what's called gravity center. We said last time that typically at the very beginning, when the limit cycle is kind of symmetric and round, the gravity center is going to be right on the branch of these of the equilibrium states, right? Then when the transition further away from the bifurcation, then you never know what that average curve. Again, this is it's called space curve or spatial curve in 3D. It's a curve in 3D, how it's going to look like. But in the case when you're going to end up through the Andronov bifurcation, it's known that the period of the periodic orbit increases infinitely. It becomes infinitely long at the Hammer-Klinic bifurcation, which means as this, say, green orbit, right, or the purple limit cycle gets closer and closer to the saddle, then the gravity center is going to move from the middle in a cycle, right, towards this point, because you're going to spend more time near the Hammer-Klinic bifurcation. So it's going to overweight the rest of the contribution of the average equation. So the no surprise is going to move like this, okay, and we need this, and we need this. And at this point also we assume that the slow null line, which is this orange plane, is placed between this above the knee point and strictly below the Hammer-Klinic point here, right? Again, this is not a Hammer-Klinic bifurcation in the full system, it's a Hammer-Klinic bifurcation in the fast subsystem. So the way you move, you start here, you converge to this branch, then slowly transition towards the knee point, and then you take off, land on the surface, right, and keep moving around until you reach the end of the Hammer-Klinic, the end of the surface, right, and then from that surface you transition back to this branch. So from mathematical point of view, this is interesting because you can have, again, I'll show you today that you can get onset of chaotic dynamics right here at the transition. Okay, and we're going to talk about this more, right? And more importantly, I'll tell you how the position of the slow null line changes the types of the activity that you can observe in that system. Okay, so the next example is very similar to what we just discussed. The only difference is that you look at the sum of the eigenvalues at the saddle on this branch, right? And you find that the so-called saddle value of the fast subsystem, basically the sum of the eigenvalues at the saddle, it's positive, right? Which basically means that the stable branch, okay, this inner surface, it cannot terminate through the Hammer-Klinic bifurcation at the saddle. It's just not permitted, right, anymore. Unlike the previous case, right? What happens is typically, again, this manifold is going to rock back like that, and then it's going to terminate at the Hammer-Klinic bifurcation. So this purple surface, by construction, is made of what's called repelling unstable limit cycles in a fast subsystem. But other than that, okay, if the surface is still kind of in between the knee point and this point, then everything is, even not the even point, but this fold on a surface, right? Then you're gonna get still square wave bursters. But the question is that, I mean, can I get just tonic spike in activity in a cell? And then clearly, that's what's the most interesting part of the story here, right? And the last case, hopefully, that we can consider at the end of this class, right? Again, let me just say that the PDF of this lecture, I uploaded it to the Dropbox, and you're supposed to have access to that Dropbox. It's called Lecture 4. So in this case, okay, what happens, you move, again, in our terminology, this is called delay loss of stability. So delay loss of stability basically means that the two-dimensional surface, also it has this characteristic fold, but it's characteristic fold due to what's called the Bautin bifurcation. Bautin was a student of Andronov, so he considered the case when the limit cycles, a pair of limit cycles emerges from nothing. Okay, sometimes people say from the blue sky or out of blue, but again, blue sky catastrophe is reserved for something different, and hopefully we can also address this today. So you have a fold here, right, and then the surface continues, but again, we want to make everything compact. So the idea is that we need to design the Z equation so that when you start over here, when this branch is stable, you converge to the equilibrium state, then you slowly transition, right, through the Andronov-Hopf bifurcation, and then you now on an unstable branch, right, which means that the equilibrium state here is unstable, and if you add up a little bit of noise, right, then it's going to diverge from the unstable branch, and it goes onto the top surface, right, immediately. So still there is these kind of overlap here between the branches. So, and then it's supposed to transition back to the fold, right? So Z prime dynamics should be negative in this direction, right? And the way it's designed is it's very simple, right? So basically you've got something like this. I mean, again, what I forgot is I have to multiply everything by epsilon to make sure, and mu doesn't have to be small, it has to be just mu is just radius of the cylinder, so that inside the cylinder, Z prime must be positive, right? And then when it happens to be outside of the cylinder, for example, on a limit of this green periodic branch of limit cycles, right? Then you transition back to the fold. So it's a simple design, okay? And the way, again, you can do that clearly, right? This is very close to what's called a normal form for Andronov bifurcation. This term is going to give you a limit cycle. Okay, this is called nested limit cycles in a limit cycle. It has to be unstable. That's why you want to make sure that this coefficient is positive. And you make the other coefficient quadratic, not quadratic, the x2, what's the quadratic term, right? You want to make sure that's negative. That will give you the stable limit cycle as an outer attractor. Okay, so that's how you can design it. And then I'll show you later on the model where you can see everything, how it works, right? Again, so the very first model is due to these two gentlemen, Hinmarsh and Rose. And as I said initially, that's the equation of the model, right? It has fast variable x, y, and z is slow due to that small epsilon. Okay, that's what makes it slow or fast. Also observe that the z term in a first equation is very similar to the Pitskin-Aguma case, right? It's just it's not a quadratic term, not a cubic, just a linear term in here. And then the z equation also, you see, it's linear like Pitskin-Aguma. Okay, so what's the deal here? The deal is that initially they derived, again, I guess none of them was sort of great expert in dynamical systems, but they were interested in what's called mathematical biology. So they created a model that would give you a single spike like this, right? They didn't think about designing a burster, right? And somebody later on told them, yes, some cells, right, can be endogenous bursters like that. So they produce what's called a square wave burster. So you need to extend your model and make it three-dimensional. And that's what they did. And of course, because they're mathematicians, they added up the third equation and they made it as simple as possible, which made it linear in all arguments. For us, it's a great simplification, right? When we're going to talk about what's called averaging method. So, and depending on some properties of the fast subsystem, right, you either have, so that again, as I said, the topology of the manifold is determined by the fast subsystem. If you play with this coefficient, you're going to get either Andronov-Hopf bifurcation far away on the left, right, or it's going to be somewhat like that, right? Instead of ending through the Hamiltonian bifurcation, right, the surface ends up through the reverse Andronov-Hopf bifurcation, and we'll get plateau-like oscillations or something like that. And of course, there is an intermediate case when you are right on the borderline. So as you can see, when you're right on the borderline, then some bursts, square wave bursts, right? Then like plateau-like oscillations, right? And then you see square wave bursts again. So it's typical when the system is on the borderline between, say, square wave and plateau-like case, right? So clearly, basically that surface that looks like a bullet-shaped surface, it basically touches the cell branch over here. That's what happens. Okay, so then we go back to the equations, and again, how this low fast system typically attacked, right, or they're addressed. So basically, what you do first, right, you would make epsilon zero. This is called singular limit, and then make epsilon zero. Z prime becomes zero, which means z becomes a constant. Therefore, z becomes a constant, right? And then you use z as our current, which is basically the same thing, right, to find, we said, these critical manifolds. Okay, so critical manifolds is the manifolds around which the full system, when I say full system, I make epsilon small but positive, right? And the dynamics of the system is kind of focused around these slow manifolds, okay? And then you're going to get Andronov-Hopf, change z, right? And then you extend it, and then it terminates to the Hamiltonian bifurcation like this, right? In this case, right? Or it can be reverse Andronov-Hopf bifurcation, somewhat like that, right? And then you follow the limit cycle, this green limit cycle, right? And as you can see, it approaches settle closer and closer, and that's why the period of this limit cycle grows from, say, 10 to 110, 10 times. It's called tenfold, right? It's a lot, right? So which means the period of this limit cycle grows very quickly. Okay, you use what's called ln fitting. So to demonstrate that really the period obeys this law, which means it's a truly Hamiltonian bifurcation. Okay, and that's how you can prove that, right? Plus, as I said, again, computationally, you have all these coordinates over here or in any cross section, and then you can do the averaging. So in this case, I mean, x is a vector, so which means you average x and y variable, right, at the same time, and that's going to give you for each given z, right? And then you change z, and then it will get this line that starts off from the Andronov-Hopf bifurcation is going to terminate over here. That's what's called averaging, but it's a simple averaging, right? So basically, what you can say instead, now speaking of Fitzhugh-Nagumo. So basically, you can say I'm moving, okay, over here between this unstable branch, right? And instead of saying that I'm jumping on a two-dimensional surface, you can say I jump on average. I jump on that green line. Okay, that terminates with the Andronov-Hopf bifurcation, and from that point I jump now on a blue line, right? So which means Okay, if you use averaging, right, you don't have to average equilibrium states because equilibrium state itself is an average system, right, so to speak. But then this is going to give you how the idea how you move along this two-dimensional manifold, right? And again, the center of the gravity of your point is going to move along that average curve over here. Okay. So now, what I did when I became interested in a slow fast neuronal system, right? My first contribution was that, all right, I don't want to even consider the singular limit, so I don't ever vanish this epsilon, right? I consider the whole system, right? I examine the bifurcation in the full system. What's the deal? The deal is that, okay, so the gray line, the gray plane that you can see here is basically, you see this equation, z equals s x minus x naught. And x naught is just a constant parameter, which basically, okay, so x is here. X naught is going to shift, okay? That used to be the orange plane, now it's just a gray plane. Okay, it shifts it up and down, okay? And what you do here, if you would like to detect this S-shaped branch of the equilibrium states, right, all you have to do is that, okay, still, the intersection point of this line is indeed that you're trying to find is occurs, right, right here, okay? And what you do is that you find this equilibrium state and then you shift, okay, and then you shift it along that branch, right, and then kind of you trace down the blue line, okay, and then if you shift it up, then you're going to trace down the branch of the equilibrium states, right, as an intersection point of this plane, right, and with the desired space curve that you're trying to identify. Okay, and now let's look at the eigenvalues right here. Remember, before in the Fitzgerald algorithm, this branch was stable, okay, and what was shown here, this blue, red, and green. Green is the eigenvalue of the equilibrium state due to the z equation. So it's shown small, this green dot, which means again it's due to the epsilon, right? So therefore this branch is still stable, okay? So you have three eigenvalues in the left open half plane in a complex plane, right? And then when you approach, when you move this plane up, then either blue or green dot, which represents the eigenvalue of the cell of the equilibrium state, come closer to the green point. Can I, guys, just a sec, right? I pick up the phone, my mom's calling. Mom, я лекции сейчас. Ага, пока. Извините. Okay, and then this becomes complex conjugate, right? As you move up, they cross the imaginary axis. So basically, in the full system, this fold represents the Andronov-Hall bifurcation indeed, right? And then they cross the imaginary axis, right? And then becomes now they have a positive real parts, right? And then as you move away from the fold, right, they land on the real axis, right? And then they split. So this point, this branch between these 2 points actually is made of, remember we said it used to be unstable. Now we have to say these are the saddles, and these are the eigenvalues of the saddles, right? Okay, and by construction, remember that the cylindrical surface ends up through the Andronov bifurcation, or through the Hamiltonian bifurcation. So when I look at the blue and the red dot representing the eigenvalues of the saddle in the fast subsystem, the sum of blue and the red dot should be negative, right? That's why, again, that's how we claim that the surface is going to terminate through the Hamiltonian bifurcation. Okay, and then if you move up here, okay, what you see is going to be something funny, right? So when it happens to be, let's start over here before the Andronov bifurcation, okay, in a fast subsystem. So when we have an equilibrium state here, it has the green dot, okay, so this branch must be stable, but this time, because the Andronov bifurcation occurs in a fast subsystem, then these fast or these dots, these eigenvalues, due to the fast subsystem, these guys, right now they're in the left open half plane, And now they ignore the green dot and they transition towards the imaginary axis and crosses, and this would give you the Andronov-Hopf bifurcation. So on the middle branch, okay, between this point and that point, right, you have eigenvalues green dot on the left, and then two eigenvalues in the right half plane. So it's a saddle focus, but again, we can't reach it because it's surrounded by the cylindrical surface. So that gives you the idea how the eigenvalue transition, right? But with different values, and we're going to talk about this too. But the middle branch over here, it's surrounded by the cylindrical surface, so we don't really see it well at all, right? We can't see it. So we can see it here, right, and then move like that, and that's what's going to happen. Okay, so to illustrate my point, okay, let me do this, right? Before I move forward, okay, I'm going to show you something. You open up this file, right? In a Dropbox, we have a shared folder and then M files, and one of them is called Hinmarsh. You go to the Hinmarsh ROS folder, which is HM, right? And it's called Neurons Law, and you just run it, click it, okay, and then you're going to get something like this. Okay, I can zoom this in. So what is shown here, I start on the left hand side. Okay, so I'll just show you the picture. Okay, that's the one. And where is the window? Right here. Okay, so you can see I pick initial point on the left hand side from this Andronov-Hopf bifurcation. So you can see my trajectory transition towards the stable branch, right? But you can see how I transition. Then clearly these are delay of stability, right? And then you can see that kind of glass Rümke-shaped surface, right? And then it basically lets you visualize the cylindrical surface, right? And then you come closer to the very end, okay? And what's shown in red here is what you see when you get to the end of this bottle or that glass of. All right, and then what you're going to see, this is voltage in time, okay, and this is just showing the projection onto, it should be X and Z axis, so ignore that, it's not Y, okay, and this panel, you can click on it, you can click this, right, and it's a two-dimensional projection, and this is a three-dimensional surface, right, as you can see, transition, right, and something at the very end, we're going to talk about this. At the very end, this dark area is shown in red on the left hand side. So when I look at the code, this is my value of X naught, as you can see it, right, the shift, okay, and I can move it up and down. I'll show you later on, right. Then the equations themselves, this is epsilon, and then I integrate for some period of time, and I'm using what's called ODE15S solver. S stands for the Steve system, but Steve basically means slow or fast. So it basically use this ODE solver to integrate slow or fast system, okay? And then you plot in panels 2 and 4, this and 2 and 4, the transition, right? And then you pick the very last point over here of integration. Let me see this one. It's called S and X, Y, and Z. And then you pick the last point as the first point and integrate again for a shorter period of time, right? Just to show this transition and that transition, right? And basically, this is the time. If you change that, you're going to get fewer points over here, okay? So, and then also what I can do, I can remove this value, okay? No, not this value, the other way around. If I get rid of that, then you will see it's going to be between 0 and 600 from now on. Okay, from 0 and 600. And what you can see, these are the bursts. And no surprise that, look at this, I have 2 spikes per burst, then 3, then 4, and then 3 again, 3 again. So this corresponds to some kind of chaotic bursting in the system that occurs right at the transition when it transitions from tonic spike into bursting. Okay. So let me show you. I'll come back to the simulations later on. Okay, and let's talk about what's called true averaging. Okay, so that's a very important technique for slow fast system, and that technique was originally proposed and developed by Pendragon. Pendragon, he was a great mathematician, right, in the Soviet times. I have no idea, honestly, who Radygin was, but very likely Radygin was his student. And what's the point? And the point is that, okay, the idea is the following, that, okay, the x and y in a singular limit, right, they're going to give you a periodic orbit. For example, let's say that this low null line, you move it up, okay, so that this gray surface where z prime equals 0, it cuts through the cylindrical surface, right? Okay, and it cuts through the average curve, okay, this one here, right? And my point is that the center of the gravity of this periodic orbit is right on that average curve x in a three-dimensional space, okay? And the way you do it is that, suppose again you analytically know the equation of that limit cycle, which is again parameterize it in time, right? And then what you do, you plug equation of the limit cycle, again analytically or numerically, into the slow equation here, right? You plug it right here, because you see that you don't need y, you need only the x component, okay? And then you average it, okay? And then if you do it in a singular limit, then basically this limit cycle, right, in a single limit is going to be just a line segment like this, right? So it has no width in z variable. It's true for when epsilon 0, epsilon is small, okay? And once you've done that, you have what's called an average equation. It basically tells you this average equation, you integrate it average it over the period of the limit cycle, right? Clearly, it's a function of z. So period here and period at the very end is going to be different. And the idea is that this period, okay, this period is fast enough compared to the characteristic time in z. So which means z variable, z dynamics shouldn't be should be way slower than the fast dynamics. Okay, so the reason I said that, because the averaging, this way averaging approach, fails to give you the answer at the very end of the Hamiltonian bifurcation. Remember, the period of the periodic orbit, it increases without any bound. It becomes infinitely long, which means it becomes on the same time scale with the z dynamics. So averaging fails to work right here at the very end, edge, right far away from the point everything is fine again. This evolution, turning around the manifold, is much faster. So basically, what this equation gives you, it gives you the dynamics, right? It approximates dynamic along this gravity line, okay, the average x. And the point is that, okay, so clearly it's a z is a scalar, which it's not a vector, it's just a single variable. And whenever again epsilon is non-zero from now on, right? And the zero of this function r, in this case right here, if you have that zero, that it corresponds to a steady state of the system, okay, which means it's a steady state of the full system, which means you're not moving in z direction, right? You just converge to the stable fixed point over here, and then you move like this, okay, like that. Which means it corresponds to the periodic orbit on this manifold, which again, the reason, remember I said multiple times, then if I want to get a burster, I want to make sure that this gray or orange plane is above the fold here, right, and below the termination point on a Hamiltonian bifurcation in the fast subsystem. So clearly, if I'm going to shift this orange line over here, then I'm going to get an equilibrium state here. Then I would say, by changing x naught, I can get a steady state here, equilibrium state. I can make my neuron hyperpolarized quiescent. Quiescent means rest. It's a resting state, steady state. Okay, then I transition to bursting, and then when I shift this line up, then I'm going to get what tonic spike in activity in the system. Okay, so and So the most interesting part is what happens right here when it transition. So what happens is that when I lower this gray plane, right, then I'm gonna make this equilibrium of the periodic orbit shifts towards the determination point. Okay, again, it's called parameter continuation approach. So if I want to find the cylindrical surface, what do I need to do? You're absolutely right. I need to find this orbit, okay, and slowly shift it. And then this periodic orbit is going to trace down the desired surface, right? Okay, this segment. And if I move it up, shift it up, right, then the limit cycle is going to go backwards. And then it let me find the Andronov bifurcation, and after that, the branch of the equilibrium states. So that's the meaning of the averaging approach. Okay, averaging is very important, right? So I'll give you an example. Today in Atlanta, we have temperature is around 17 Celsius, right? Should be around 3 p.m., right? Whereas my daughter lives in Washington, D.C., and it's warm today too. So, but only today. But on average, right, in the winter, they have snow, and we don't have typically snow in Atlanta. We have it just for a few days, which means on average, our temperature is higher than temperature in DC or in New York, which means we have different trees. We didn't have different grass. Okay, so for agriculture, average temperature is important, right? It's more important than peaks of high temperature. In Russia, Nizhny Novgorod, summer could be very hot, but the winter is cold as well. So which means on average temperature could be around 0, right? Whereas here the temperature on average is positive. Okay, so that's when you deal with something that changes periodically or in cycles. Okay, averaging is the most important tool ever. Okay, you always have to find what's average temperature is going to be, right? I'm not talking about average temperature of patients in the hospital, right? I'm talking about this averaging technique lets you identify limit cycle, right? And find what's going to happen. So that's the idea. Okay, so then, okay, I made that point, and then I'm going to click here onto this slide, run it again. Okay, so that's what we expect to see. Okay, question is, can I see the surface better? Okay, what I'm going to do, I will try to make that epsilon 4 times smaller, so it's a 0.002, and run it again, hoping that, but all of a sudden I don't see it. Why is that? Because basically what's happened is that I converge to an equilibrium state so quickly, right? Then I'm sitting on the equilibrium state, and the Andronov bifurcation is supposed to be right here, but this is called delay loss of stability. I'm converged to it so fast, right? And so accurately. I'm sitting on this branch, and I don't even notice when I have to lose the stability, right? I don't notice that. So to remedy the situation, either you have to add up some noise in the system, right? Okay, let's make it 0.006 to see if this can help us. Okay, now it does help us. Okay, so what I'm gonna do, still, I wanna make sure that how can I see the bottle, right? I know the Andronov bifurcation has got to be around here. What I'm gonna do is I'm gonna change the initial conditions. So I have 0 and 0 for the X and Y, negative 15, this is for Z, so I'm starting around here. Let me make it, say, negative 12 or negative 11. Just see what's going to happen. Do it again. All right. You see, I no longer converge to the branch of the equilibrium states, but more or less to the branch of the periodic orbit. And now I'm going to make it small again, just to see if I can see the better this bottle. Okay. Now, as you can see, I do converge to the bottle around this value. Okay. If I'm going to make it even smaller, can I see it better? Well, you see, basically making it smaller, I decrease the step size in Z, and now, okay, I have so many points so I can barely see through the surface, right? So therefore, what I'm going to do, I'm going to change initial conditions and make it negative 12. Okay, keep it 0.2. We run this. Yeah, I mean now, more or less, I can clearly may imagine where the Andronov bifurcation takes place. It takes place around this point, right? But you see what I've done is that I also make that epsilon smaller, which means my burst gets longer. You see it? And then they're no longer chaotic, right? I mean, more or less, I don't repeat the same steps. No, actually, after one evaluation, let me increase this, and I'm going to make it 1600, and then we run this. Okay, so therefore, I get regular bursts, right? Again, what decreasing epsilon means, making epsilon smaller, that means you transition slower along that buttle, right? And then you transition slower along the hyperpolarized quiescent state branch, right? So that's why you've got more or less a regularized burst. So if I go back to 0.8 and we run this stuff, then I'm getting my chaotic dynamics back, right? And okay, which basically means that making epsilon smaller, you lose chaotic dynamics, and you may wonder that in a truly slow fast system, when epsilon is really small, you don't have chaos. The answer is no, you still have it. But again, the region of chaotic dynamics, they shrink proportional to this epsilon. If epsilon is really small, the region of chaotic dynamics is going to be small too. So let's leave it like we did it before. Okay, so for your convenience, right, I just want to make sure when you download the files, everything is normal. Okay, so the same initial conditions, we run this. Okay, that's where we restore the status quo. And then let's look at this file. Okay, it's a similar file. Okay, and then I prepared these numbers for you. Okay, and let's talk about this in a second. And that's going to be your project actually, right? So I click here. Okay, so I start on the bottle. You see, I move along the bottle, come to the end, and then okay, the red line here in this projection is the position of this slow null climb, z prime equals 0, and that's where the equilibrium state takes place, right? Okay, and if I comment this out, okay, no surprise, you can see this. You see the oscillations converging to the equilibrium state, right? And now you see it's kind of almost flat, right? Compared to the transfers to the two-dimensional critical manifold. Okay, and I comment this out, run it again. Okay, and then, so what do I have after I finished integrating? Let's look at this. I have a single spike per burst, right? This is the corresponding orbit. Okay, I'm gonna comment this out again. So I shifted up. You can see I shifted up. Oh, actually, yeah, I shifted up because of these negative signs. Now I have two spikes. Okay, and that's basically that's what you're supposed to do in the second part of the project. You're going to study transitions in the Hindmarsh-Rose model. So this note I'm going to stop, right? I'm not going to do it for you. I just pick some numbers that could be helpful for you to play with, right? But then still you have to tell me, report on your findings, what you see, whether it's a tonic spike, and how would you describe chaos in the system, and so forth and so on. So I'm going to close this down and close this down, okay? And then I'm going to go back to the slides. So we figured what's going on in the system. The problem is that that's what we're going to find out next is how the transition from tonic spike in activity, right, like this, how this transition through what bifurcation mechanism of transition from tonic spike in activity to bursting activity in the system. Not in this particular system, but in the typical square wave bursters. So what happens right at the very end when you push the stable limit cycle by lowering this null climb, right, shifting it down, when you push this stable periodic orbit towards the termination point, what happens at the very end? And that's what we should discuss again, but it requires some knowledge of Hammer-Klinic bifurcation. I will just try to outline to you what happens. Okay, so again, x and y are fast equations, right? Z is a slow equation, okay? So when epsilon is 0, right, in a limit, okay, you see that blurred curve? It's basically where the two-dimensional cylindrical surface terminates. But then you make epsilon small, but finite, right? And then you look at the eigenvalues, and what do you see? Okay, you have a three-dimensional system, right? And your saddle has one positive, one negative eigenvalue, right? And two positive on the right-hand side. So if I remove the green one, okay, then I can see the fast subsystem, and I can see that some of these eigenvalues is really negative, and this basically guarantees that stable limit cycle is going to end up through the Hammer-Kleeneck bifurcation in a fast subsystem. But now you have a full system or whole system, right? And this green dot changes the game, changes the rules of the game, namely. All right, so originally the Hammer-Kleeneck bifurcation was, this theorem was done by, again, my dad, Leonid Chilnikov, who basically, what you have to do, you have to reverse the time. If you consider the saddle in a backward time, then negative eigenvalue becomes positive, and these two guys move to the right-hand side. But bottom line is you have to still find the sum of the eigenvalues nearest to the imaginary axis. This is called the saddle value. And what you will see that saddle value is going to be positive in a backward time, which means no stable orbit can end up through the Hammer-Kleeneck bifurcation. So that Hammer-Kleeneck bifurcation should do something to become unstable, right? In this case, it should become not unstable, but of the saddle type. Okay, so it has to transition from stability to instability somehow. And basically, what is shown here, these are different. This is how the surface, that cylindrical surface, right, that continues over there, that's how it ends up through the Hammer-Kleeneck bifurcation at different values of epsilon. As you can see, it's no longer perpendicular to the saddle branch, right, but becomes tangent to that saddle branch. And this is called, again, I do know that Dimitrov taught you something, some basics of the Hammer-Kleeneck bifurcation. And this is called Hammer-Kleeneck bifurcation. It's a degenerate case when the separatrix comes back along what's called a strongly stable manifold. This bifurcation is known as an orbit flip in the community. And its feature is that, okay, so basically this, like a sail of the yacht, right? It shows you the determination plane or surface of the cylindrical manifold. Basically it tells you that I can get. So if you have this bifurcation in a normal setup, that basically means you may get onset of chaotic dynamics very close to this bifurcation. For the periodic orbit, this basically means, okay, that if I go back to the slide, when I push it towards the end point, okay, this periodic orbit must become unstable, okay? And if you, again, some know the basics of the bifurcation of periodic orbit, then you have several options. You have either saddle node bifurcation of the periodic orbits. We talked about this, right? When a stable, unstable limit cycle eventually disappear, right? Then this limit cycle may become a two-dimensional torus, okay? But in this system, torus bifurcation cannot occur due to constant divergence of the vector field. So what it can do, how it can lose stability. And the idea is that, okay, this periodic orbit, when it comes close to the saddle, it loses stability through the period doubling cascade. And I do know that Arkasha Pikovsky taught you some basic stuff about period doubling bifurcation in the unimodal map. So this limit cycle will become unstable, and the stability goes to a limit cycle of period 2, but period 2 orbit cannot also end up through the Hammer-Kleeneck bifurcation, so it's going to be orbit of period 4, and for orbit of period 4 stable also cannot end up at the end of this bifurcation, right? So it has to lose stability, and I'll show you what what you're going to see at the very, very end. So, and where we are, here we are. So basically at the very end, you're going to see some kind of chaotic dynamics, and the idea is that in a singular limit, when epsilon is small, okay, this map, okay, x prime equals mu plus x to the nu, and nu should be greater than 1. Okay, this map in a fast subsystem should give you a stable limit cycle, because you're going to add up an extra term due to a slow subsystem like this, right? And epsilon is negative, then you're going to get like a unimodal map like this, right? And here you have, because epsilon is small, you have basically infinite derivative, and that infinite derivative is going to give you infinite stretching instability at the very, very end of this bifurcation. But what I've just said is just I outline some, just I'll outline some basic elements of the bifurcation unfolding. So I don't want to go into details at this point, but let me just show you some demonstrations, right? Maybe I should have done that here. No. Where is it? Hindmarsh-Rose model. I do it again. I open up this file, and then, okay, that's the value close to the transition. Okay, if I pick it up here and run it again, okay, as you can see, you have chaotic bursting at the very end, and then if I make this number, say 9, okay, I shift this line up. Let me see. Then, as you can see, when I shift it up, I got that desired periodic orbit at the very end of this surface. Okay, and as you can see, it corresponds to towing spiking activity. Now I'm going to shift it down a bit, right? And okay, so far, I mean, maybe I didn't integrate long enough. Okay, I'll do it again, 9, 9, and let me see. And then look at this window. Okay, I'm going to zoom this in. Zoom it, plus, like this. And you clearly see that there are 2 spikes, right? And the distance between the spikes is shorter than that distance. So we call this duplet, right? Which basically this indicative of period doubling, or the beginning of period doubling cascade. That stable periodic orbit that used to be here, right? If you integrate longer and then you don't show the transition, right? You show just the very end of the transition, you should see orbit of period 2, which will become an orbit of period 4, and so forth and so on. Okay, so this basically occurs at this value. So again, I'm going to comment this out, save it for you so you can examine the transition. And then I'm going to open another file. It's called Che. Okay, from the same directory, right? And Teresa Che, she died of cancer many years ago, and then she developed one of the simplest Hodgkin-Huxley type of model describing, again, 3 variables, right? Describing what's called excitable cells. When I refer to excitable cells, we typically mean Hodgkin-Huxley, not Hodgkin-Huxley, Fitzgerald model, right? But again, let me just run and tell you what's going on up here. Okay, first we close the window, and then we run it. So, okay, so that's your chain model. Okay, so zoom this in. You can see there is a surface, right? I transition through the surface, and then end up back to what seems to be very like in Ronoff bifurcation, right? Around the corner. Okay, that's just a single burst, right? And then oscillations toward the steady state. And in this case, right, okay, this is my current. In this case, I use external current as a parameter. I don't use any shifts here. So I'm going to make it negative 60. Okay, so you'll see for yourself what happens is that basically there's a straight line right here, and I move it up. And now, okay, now this model produces, let me see, okay, bursting activity, 2 spikes per burst. Okay, when I move it up even further, okay, then, okay, that's what I see at the very end. Okay, this is my attractor. It looks like almost identical to what I've seen in the Hindmarsh-Rose model. Look at the voltage traces. Now I have some number of spikes per burst. This is just the calcium slow dynamics. It shows you this calcium slow dynamics over here. Okay, then this is done for when current is 0. I'm going to move it up even further, make it 5.3, run it. Okay, so now you can definitely claim that I can see pretty well-developed chaos in the system, right? Then the number of spikes per burst changes. That's my attractor, okay, right here. this is the three-dimensional version of this attractor. Again, it's called eyeball expansion. Eyeball inspection. Looks like almost Hindmarsh-Rose model. And then I'm going to move it up even further. Okay. And okay. Then let me see what I've done. Okay, let me just make it wider. So as you can see, I have burst, and then tonic spiking. Let me see, is it regular tonic spiking? No, it doesn't look like a regular. So you have some kind of intermittency between the spikes, right? So clearly this attractor is still, looks like it has a move around this manifold, right? Then you're going to give you spikes, and then sometimes occasionally you make the long excursion to generate bursting activity. So if I go and say restore the view, I have a chaotic spiking for a long period of time, and then it interrupted by this burst again over and over, and then that's basically what happens. But if I make this number, I'm going to comment this for you. I'm going to make this current, say I equals, so we need to decrease it. No, it was 10. Okay, increase it 20, which means, remember, we shift this manifold to the right. Okay, let's make it 20. Run this, and eventually, right, everything converges to a limit cycle, a periodic orbit, almost a periodic orbit. Okay, so it doesn't look like regular, but if I make it 40, I should see more and more stable limit cycle. Yeah, it looks like it's stable limit cycle. Not yet. Okay, still I have some. Okay, let's make it 140. Okay, just don't kill the neuron. Okay, 140. And if I do 140, then yeah, looks like I have a limit cycle at the very end, no oscillation on calcium converging to the steady state, and basically that's the idea, right? What you can see. So this model is called a J model, right? You're welcome to find this paper and review it. It's a good paper. Again, you have three-dimensional system, you have a voltage, and also you have a calcium and then fast sodium channel current to generate spiking activity. Okay, now I'll show you another file. This one is called Che Events 1D Map. So basically, let me do this. Also, I have a number of external currents. Before it was just, it was just not hue. I'm going to close it, Che. In this case, it's called just a current. Here, it's called external current. And what I'm going to do, I'm going to run it. It's going to take longer. I integrate longer. I transition. First of all, I remove the transient. I integrate for 50 units of time. Then pick the last point, plug it as a new point, initial point of the integration for this period of time, and then I'll show you something. And now you have two windows. Okay, and that's how you numerical way of computing was called Poincaré return map. That's what you discussed with Kasha-Pikovsky, right? So what happens? What I've done is that in this voltage traces, okay, I'm gonna find the points over here. Let me just zoom this in to show you over here. So I'm finding the points, okay, even more, where voltage right here, right, is minimized. So that point, these points, these points. Okay, let me stretch it out so you can see better. Okay, I'm going to find these points here, where voltage is minimized here, here, there, right? Okay, and then I just highlight the points on a attractor so you can see these red points. And once I found this point, I mean, you're welcome to try this. Again, I add up an extra function in MATLAB code right here. And now you see that I find V mean, the minimal values of voltage here, right? And I collect all these points, okay? And I have a set of these points, and then I play a single trick here, okay? Let me see, where is it? Okay, I have a long array of V minimus, right? Right here, say I have no idea how many. Let's say 1,000, right? And then I use this trick, right? I do what's called circular shift. I shift all these points to the right but it's a circular shift, which means the first point becomes second, second becomes third, and 1,000 point becomes the first point. Okay, and after that, I plot Vn points versus Vn plus 1. As a result, I'm going to get a map that looks like this, right? You can clearly see how the map looks like, right? Where is the intersection points here? There is a one intersection point here, and if the slope at this point is steeper than -1, that the fixed point is unstable. Okay, these points over here, right? They correspond to these quiescent phases over here. Okay, they look like. Okay, and then you have a one-dimensional map, and you can do either approximate it, right, analytically, or you can study it numerically. So let me see. But the fact that I have a negative derivative here means that I'm very close to the period doubling cascade. Okay, so again, it's going to be part of your second project. Okay, let me just comment this out. Okay, or I'm not going to comment this out. I'm just going to make it say 7. Okay, just some random numbers that I have no idea. All I know is that I have to make it larger. Okay, we talked about this before, and then I wait long enough, and then eventually, okay, as you can see, I'm moving towards tonic spiking activity, and my map only has a few points. Very likely it's just due to period doubling, so I got to be very careful. So it was 3. Let me just find something intermediate between the previous value. It was 3.4, yeah, 5.4, 7 way too much, right? Integrate on your laptop. It's going to take some time. And then you will see the evolution of the return map for the voltage, right? You see now it has again this cusp form, right? It's not as cusp as used to be like this longer, but it gives you an idea how this one-dimensional map changes as you change the external current, right? And let me just tell you that what's going to happen then, it becomes less steep, so that drop is going to be not that significant, it's going to be shorter, and then right here you're going to have a period doubling cascade. So no surprise that in a Hindmarsh-Rose model and in a chain model, when you transition from tonic spiking activity to bursting activity, then both systems undergo the period of doubling cascade, and after that you have bursting activity again. But this occurs within a very short period of time, or short interval in parameter values, right? And this is one of the typical transitions from tonic spiking activity into chaos in neuronal system. And we're going to talk about this more. So that's another file. So tomorrow, once I give a talk at the conference, right, I'm going to shoot you an email specifically telling what you need to do for the second part of the project. Okay, so let me restore the status quo. I'm going to put 3.4, so you have these numbers handy, so you don't have to invent. Okay, but nevertheless, you need to study on your own and perform your own research about the bifurcation occurring at the transition between activity types in neuronal models. So let me see. I want to make sure that I'm back to normal. Okay, that's your drop, period doubling cascade, and I'll demonstrate even more and more that this is a very typical one-dimensional map, generic for most for most square wave bursters. Okay, and if you ask me why it looks like it's one-dimensional map, and again because of the slow subsystem and because of the strong contraction, so it doesn't have to be one-dimensional, right? The truth is that it's a fractal. It looks like these points belong to the same line in this particular case. So I'm going to close these. I'm going to close that. Closed and close, right? And then we consider something different later on. Okay, back to our slides. Okay. Now let's talk a little bit about, again, this bifurcation knows as the cell bifurcation. So, okay, for a reason I use z variable instead of x, right? Because again, z is going to be the slow variable in a Hindmarsh-Ross model. And let's say that, okay, so I go to, let's say that in the z-axis, right, I did my averaging, right? And after I've got an averaging, then the function on the right-hand side, let's say it has this quadratic tangency, something like that, right? Okay, which means that I have a stable equilibrium state in the system and an unstable one. But don't forget that this is assumed to be the averaged equation for the periodic orbits, which means this guy, this blue point, is actually a stable limit cycle or stable periodic orbit on that two-dimensional manifold. And this point also, it's stable in x and y, but now it's unstable in z, which means this point corresponds to the saddle periodic orbit on that manifold. And then they both merge and disappear, and that's the time that you need to get through the ghost of the cell node. And the dominant term at this transition, clearly 10 is bounded, right? It's due to reciprocal of a square root, right? And a minus a node tells you how close you are to the bifurcation. Okay. All right. So same story, right? Same illustrations. Okay. Then saddle node in an average slow equation, but then I consider the full system. I don't have to look even at these guys, right? Again, 2 points. Each point corresponds to a periodic orbit. Left one is stable. Remember, the surface by construction is stable in x and y, and the second one is stable in x and y, but it's unstable only in z. So this saddle periodic orbit is unstable along the two-dimensional manifold. Okay, and then I bring them together so that they merge, okay, into the saddle node periodic orbit or a double periodic orbit, right? And that double periodic orbit, it inherits this unstable two-dimensional manifold from it, right? Okay, then these two strongly stable manifold collapse in one, and everything that starts on the left from this strongly stable manifold converges to the periodic orbit, which is stable for all trajectories on the left from this strongly stable manifold. And then you transition further beyond the bifurcation, and equilibrium states disappear in a slow fast system average equation, right? And then you have some kind of this kind of ghost of the periodic orbit because it takes you time to get through the cell node. And again, that's what you should see really, right? So you approach very quickly, then stagnation area, bottleneck effect, you slowly transition through the area, then speed up, and then run away. But again, we don't run away just anywhere on the right, but then we create a mechanism of reinjection, reinforcement, and place this trajectory back onto the track, right? So it comes back from the left, okay? So that's what we're gonna do next, right? Okay, and the way it's do it, right? Now, this is known as example that was designed by Leonid Shilnikov and Dima Turaev. This is called the blue sky catastrophe, right? So what's the deal? The deal is that you have this periodic orbit of a cell node type, right? And then let's say in 3D for simplicity, and this is two-dimensional unstable manifold, right? And then you envision the following, right? So instead of running away to infinity, right, somehow it gets bented, right, and re-injected into this area which is called nodal or stable region of the cell focus, right? So that construction, sometimes called a French horn, right? So that pipe gets narrower and narrower as it approaches the cell node from the left. And when I say it gets narrower, meaning that the local map here is a contraction, which means as this periodic orbit disappears, then you have a single stable periodic orbit that emerges from that construction. And there was a picture from my paper with Gavrilov, right? So don't be fooled by the thickness of this periodic orbit. It's not meant to represent a pipe, but a stable periodic orbit that has this global handle, right, and then many turns around the ghost of the solenoid, which makes this periodic orbit infinitely long in length, and also it makes it infinitely long in its period. Okay, so that's what's called the blue sky catastrophe, right? It's a solenoid bifurcation. It's not only local but global, and then it results in a stable periodic orbit of infinite length and a period. Okay, so how we manage that solenoid bifurcation in a Hindmarsh-Rose model? Okay, so again, let's go back to basics. Z variable, y here, x and y are going to give you that two-dimensional critical manifold along which transition towards the homoclinic bifurcation. Okay, and what you do is, okay, remember what I said, that the Z equation, average, right? On average, it describes the dynamics around this manifold, but not around this manifold, but around its gravity center mass, right? Or line, this one, X. Okay, and if you transition from this point, okay, so moving through this along that line, right? And my dynamics is determined by the Z equation, this one, and I add up an artificial term, okay, like this, A, and then you see in the denominator I have Z minus Z naught. Z naught is going to give me basically the center of that bump, okay. A is going to give me its magnitude, right? And I add this term to make sure that I don't have 0 in denominator, so I don't want to have any approximations, right? So basically 0.03 is going to give me the width or the thickness of that bump, right? So by playing this constant. And what I've done is that then I change A, and okay, when A is large enough, then this bump crosses this average curve X twice here and there, and this point will correspond to a stable limit cycle like this, periodic orbit, and this would correspond to unstable periodic orbit. And when I lower the bump and I have a tangency, the tangency would give me this solenoid bifurcation, right? And after that, if I lower the bump even further, I can transition through this line or through the surface, okay? But if I keep this gap small enough, that's what I'm going to see. You see, I'm approaching very quickly. Clearly that epsilon here is not really small. If I make epsilon small, then I would lose the stable branch right at the knee point, but epsilon clearly is large enough, so you see that how you move, right? So you don't converge almost immediately, right? You kind of become tangent to that manifold, but you can change it by decreasing epsilon, and then you transition, and then above this yellow bump, right? Yellow surface, you go to the right, below you go to the left, and then I regulate the gap between the bump and the average curve, right? So I make it smaller, and I quickly approach the stagnation area bottleneck effect from the left, and then I turn around, and slowly transition, right? As a result, I'm going to get many spikes over here before I can go back into bursting, which means I can make a burst that has infinitely many spikes, and that basically means that I can make a burst that has infinite length, right? Not only just spikes, but infinite length. So that basically gives you the idea of the how you can make the blue sky catastrophe in a Hindmarsh-Rose model catastrophe. Okay, so that's basically the idea. And then later on today, I'll show you that you don't have to, reinvent. Don't have to invent some crazy bumps, right? In a slow equation, but it will occur naturally in one particular Hodgkin-Huxley type of model. So which makes it generic bifurcation that describes transition from tonic spiking when you have a stable periodic orbit here to bursting through the blue sky catastrophe, right? So no surprise that most recent textbook on dynamical system, they use my examples, right, and my results to teach dynamical systems and mathematical neuroscience, right? Exactly through this bifurcation. Okay, so what I can do though, all right, so don't be fooled that basically what I've done here, I take this picture and rotate it through pi, so which means this fold will be on the right, like shown here, okay, and this is the end of the bifurcation. I just changed the viewpoint in 3D, but still I have this bump, okay, and let me just show you the following, right? So I made that bump large enough, so that means I have two intersections. As I said, the point, this one on the right here, right before it was on the left. Now it's a stable periodic orbit, right? And if I happens to be on the right from the stable periodic orbit, then I will converge to it along the two-dimensional manifold. Okay. Then the second point here, right, is unstable in the z equation, but stable in x and y, which makes it a settled periodic orbit on this manifold. So, and this manifold has two-dimensional stable manifold, right? Basically it's a disk like this, right? And if I happens to be on the right from the disk, just imagine this, just a separation line or the surface. If I happens to be on the right, I'll converge to the green orbit. But if I happens to be on the left, then I will be repelled, right, to go back. Actually, I'm moving on the left. I will be pushed towards the end point, termination point on the manifold, go into quiescent phase, right? Then we'll try to get back. I will try to converge to the green orbit, but then the saddle orbit will push me back, and as a result, I have bistability in the system, okay? So I have bistability in the system. If I happens to be on the right, then I have tonic spike in activity. If I happens to be on the left from this settled periodic orbit, then the same system for the same parameter values will exhibit bursting activity. So it's no surprise that if, okay, as I did before, if I change the position of z0 point, right, I can shift this bump on the left, lower it over here, then I will get the blue sky catastrophe. So you see that's how you can manage both cases, either blue sky catastrophe or you can make your system bistable, okay? Now, what time is it? 1 hour, 6, yeah, let's make a break. This is the chain model that I discussed before and run MATLAB experiments again. Let me just comment on that, and we stop the very first part of the lecture. Chain model, it's a Hodgkin-Huxley type of model. Let's read what it says here. Voltage, okay, voltage, and then you have, okay, so look at this. N, you don't have N here. You have M infinity, H infinity. This is called sigmoidal curve. Okay, we talked about this. This basically tells you that silicon carbide inactivates almost instantaneously. So you don't have differential equation for the M or H variable. So they're very, very fast. They don't need differential equations. They're almost either 0 or 1. Okay. Then you've got N finally, right? And this stands for the potassium current. Potassium current, remember, when potassium channels opens up, then the potassium ions rushed in to create the second part of this spike, right? It's called repolarization. And the first equation stands for the sodium. It's in charge of the beginning of the spike. Okay, so it's almost instantaneous. As soon as you reach a level over here, synaptic threshold, not synaptic threshold, sorry, the level for sodium channel around negative 45 millivolts, the channel opens up and then sodium rushes in, right? And then it closes at this value, right? And then potassium opens and potassium now rushes, did I say rushes? Yeah, it rushes out, I'm sorry, right? Because potassium is positively charged, which means voltage goes down because, again, you're losing positive ions, right? And this is a C. This stands for the intracellular calcium concentration. Okay, it's another term, and basically in this case, this rho, I don't see it here, but rho is small. If I'm not mistaken, it was kind of 10 to negative 3. But this basically makes this low equation, right? And also it's in charge of this variation in calcium. So, and then they create either, if you don't have variations, right, then you have a tonic spike in activity. If you have a little bit of variations, right, you're going to get period doubling. And then if you have long variations like shown here, then you have chaos in the model, right? And at the corresponding voltage when the system is chaotic is going to look like this, right? Or as shown here, then how many points you've got? 1, 2, 3, 4, which means the point that used to be stable, right? First of all, undergoes period doubling cascade, becomes period orbit of period 2 stable, right? And then the orbit of period 2 becomes unstable and generates stable orbit of period 4. So what you see here is an orbit of period 4. 1, 2, 3, 4. Okay, let's stop here. Let me get my team. And we will proceed in 10 minutes, guys. And there we are. I lost you. No, here we are. Okay. So I'm gonna